Okay, so good morning, everyone, and we're having our 15th lecture for the PAASE webinar series. So again, the webinars are brought to you by the Philippine American Academy of Science and Engineering, and it's really meant to feature our members and their fields of expertise. So for this morning, our lecture is entitled Ignorance in a Quantum World. Our speaker was born and bred in Manila, and she holds the BS Applied Physics magna cum laude and MS Physics degrees from the University of the Philippines. She completed her PhD at the University of Glasgow, where she was a researcher for 7 years. In 2015, she moved to Brisbane to join the Quantum Technology Group at the University of Queensland. In 2016, she took up an ARCDECRA fellowship with the same group. In 2017, she won one of four L'Oreal UNESCO for Women in Science fellowships in Australia. And in 2018, she won the Ruby Payne Scott Medal for the Australian Institute of Physics for Excellence in Early Career Research. In 2019, she won a L'Oreal UNESCO International Rising Star Grant, one of 15 awards worldwide. She is currently a senior lecturer and Westpac Bicentennial Foundation Research Fellow at the University of Queensland, continuing her mission to extend quantum information using the shape of light with her team QDITS at UQ. Let us all welcome Dr. Jacqueline Romero. Okay, Jackie, you may begin.
Hello, good morning. Salamat po sa inyong pagpunta dito sa napakaagang talk na ito sa Pilipinas. Mas maswerte kami sa Australia. It's 10 a.m. here. Yeah, thanks Kathleen for that very thorough introduction. So ngayon, I just want to talk about some of the peculiarities in quantum information. So I'll focus on this concept of ignorance, kaya ignorance in a quantum world. And before I start, I'd like to thank sponsors. So as Kathleen said, I am funded right now by Westpac Bank. And I've had fellowships from the Australian Research Council, L'Oreal UNESCO. And I'm also part of a Center of Excellence for Engineered Quantum Systems. Okay, so I made this talk really, I follow the speaker guidelines I got one time when I was invited to talk about science in a pub. So I'll try to make it personable, and unfortunately, I can't promise na walang tables and graphs because this is physics after all. I don't think it's possible. But whenever I would show tables and graphs, I think we're all will be fine because we are all scientists. Okay, so I'll start with this picture of quantum physicists. Perhaps every other person here has a Nobel Prize, and that's really your idea of a quantum physicist. Every time I'm in a party and somebody would ask me what I do, I'll say quantum physicist, and the conversation would stop. So I guess that's a society telling you na hindi pa rin ganon ka-approachable yung thing natin sa mga physicists. So actually, part of my mission as a physicist here in Australia, as a physicist from the Philippines, is really to widen the image of what a physicist is. Thankfully, in the last few years, merong Big Bang Theory. So from the sad bunch that is in this photo, parang we went naman to the other extreme. So I guess we'll see if that's for better or for worse. But what I could say is a lot of my physics students now, they watch Big Bang Theory, that I sometimes wonder whether that was part of the decision taking up physics. Okay, so this physicist, so as Kathleen said, I studied in UP. Then I went to Glasgow in 2008 to pursue a PhD in quantum physics. And then 5 years ago, I went to Australia, where I am now a senior lecturer in the University of Queensland. That's parang equivalent siya ng assistant professor. Oops, what's happening? Okay. And I have a small research group there. So we're QDITS at UQ. So our mission really is to widen the use of QDITS in quantum information. So I'm going to explain that in a bit. And we have a website, visit quantumatibapa.org. where you can find some of our adventures and definitely list of publications and other stories about the group. Okay, so my plan for this talk, I know hindi tayo lahat familiar with what quantum information is. So I wanted to start what the difference is between classical and quantum information. And then I want to focus on a recent experiment we did at UQ that just shows how different classical is from quantum information. And lastly, I'd like to situate ourselves. We hear about quantum technology, quantum communication, quantum computation a lot about these days in the news. So I'd like to just summarize where we are. Okay, so first, discuss the difference between classical and quantum information. Um, this is really very controversial. Like if you ask a quantum physicist what the difference is between quantum and classical, I really don't think there is a clear boundary. Some would say it's about the size, it's about the low energy, how cold the temperature is, but really I don't think it's well defined. But what I can see clearly is that classical information is very different from quantum information. So for me, the boundary would be more abstract in the sense that it is related to information rather than the physical system itself. So I'd like to start by asking, what is information? Um, our idea of information has evolved over the years. Like when I was a high school student in the Philippines, like information in my head would be perhaps worksheets or essays saved in my desktop, in my hard disk. But now information is like very much a part of our everyday lives. And sometimes that abstracts too much what is actually underneath, which is that information is physical. It is physical because it is carried by physical systems. For example, when we were kids and we played with this telephone cans, you actually have a sound wave that vibrates the string. So you get to hear something from your friend, and that then that vibrates your eardrum, and that gets translated to a message in your brain. So the information that we process started from something physical, and that is the physicist view of information. So now I'm going to abstract one level. So I'm going to introduce the bit, which we must have heard at some point. So the bit is what we see here, the ones and the zeros. So that's what's encoded in our computers. They from a signal like this, we can binarize them. So we have a high and low. And then when you read computer science papers, they talk about bits. So it's like everything is expressed in terms of the bits. It is the simplest classical system in the sense that you only have two states for it. Like, for example, a coin, which can be head or tails. If you think of a physical system, like one obvious one would be a spin system. Spin as in you can have a spin up, which we would call +1, and a spin down, which we will call -1. So this is, if you want to think of an actual physical system, what are spins? You can think about what is the direction that the electron spinning, or what's the electron cloud doing. But like this level, at this level is enough. We have a two-state system. We'll call it spin up and spin down. And these are usually what people in quantum information would refer to as qubits. So it's a quantum system that can have these two distinct states. So I'd like to do thought experiments with spin. So usually the question is, if you have a spin, what is that spin? What direction what direction is that. And you can think of spin. So just a little review from our high school physics, or yeah, physics 71. So a spin, you can consider that as a vector. It has both magnitude and direction. So the plus one, minus one. And it can be either in the Z, X, or Y. You can think of those as like the length of the shadow that is cast on that axis. So you can have different components in that spin. So say, for example, you have an unknown spin and you have an apparatus that will measure the spin, and you orient that apparatus such that this arrow is pointing up. Then you do your experiment, and you find that that spin, when you orient the apparatus like this, gives you a +1. So it's like you get a +1 on the Z direction. Okay, it's all good. Now, if you turn the apparatus the other way around, as you would expect, the spin that you get would be -1, because now you've rotated 180 degrees. So still no surprise there. So far, the spin is behaving like it is a vector. All good. So now what I want to do is I want to turn the apparatus like this. So now we are going to measure the vector component along the X. So surprisingly, what you get is that this one is like just randomly, it's +1 or -1. So having measured Z1 +1, we expect that the spin along this should be 0 if you think of your classical vector, right? But instead, you never get a 0 in your measurement. You never get a 0. Instead, what you get is you get randomly +1 or -1. And that's a bit surprising, because that tells you spin is not a classical vector. Like, of course, if you think of doing this many times and you average, it would be 0. So doon papasok yung sigma x equals 0. Pero at any one time na gagawin yung experiment, it's always +1 or -1. It's like the best that you can do to predict the result of this kind of experiment is really to guess randomly, which is essentially what you would do if you were completely ignorant of it, right? Yeah. Okay. So in that thought experiment, what we have shown is that determinism breaks down, although in a very particular way, right? Dapat yung average of all the sigma x events, dapat ang average niya ay 0. So it's random, pero random dapat na ang average mo 0. Just as you would expect for a classical vector. So parang a way of saying that would be, kung inipon mo yung experiment mo, you would end up with the classical prediction na ang average ay 0. But every single shot, it is either a +1 or a -1. So how do we explain that in quantum physics? We say experiments are never gentle. It's like when you do an experiment, it somehow changes other parts of that system. And that, of course, as we have seen, spin is a very peculiar vector. It's not a classical vector. So now I want to move on. So ano naman kinalaman niya sa information? Like, we know computer science relies on Boolean logic, and that is also something that, given that system, would also break down. So Boolean logic doesn't apply to the spin systems. So umpisa tayo sa this simple example. Say, for example, the speaker is wearing a blue shirt. So I'm wearing a blue shirt. So I'll give that truth value 1. The speaker is wearing black shoes. That's false. I'm not wearing any shoes at all. So I'll give that truth value 0. And then in computer science, what we do is we apply an AND gate, right? So 0 and 0, 0, 0 and 1, 0, and so on. So meron kang determined values for these truth statements. And you can repeatedly test A and B, like you can repeatedly look at what I am wearing, repeatedly look at what shoes I am wearing, and evaluate the truth values based on this truth table, and you will always get the same results for A and B. The problem is when you apply that to spins, that cannot be true. Because what happens is, say you make your proposition A sigma z equals +1. And then your proposition B is sigma x equals +1. So say you have these two things. So as we've seen earlier, so say let's do the first experiment, +1, so truth value 1. Then we do the sigma x experiment, we see it's +1. So we assign that B equals 1. We do A and B, we get +1. But then, as any well-meaning experimentalist should do, they should repeat the experiment. So I'll repeat the experiment. So A is 1 because it's +1 in Z. I'll do the sigma x measurement. Now it's negative. So now you get B equals 0. And when you evaluate again, you get different results. So you cannot apply the Boolean logic rules to spin systems. So we have to do something else. And that's what quantum information is all about. How do you process information contained in those quantum spin systems? And if you recall from your physics before, meron actually nagtatago dun sa Boolean logic na yun. Like, what if your proposition A is that the particle has position X, and proposition B, the same particle has momentum P? So now you can see, it becomes a statement. So kapag in-end ko yung dalawang statement na yan, that is a statement that's not confirmable, because we have in quantum physics the uncertainty principle. It's that statement which says if you know the location precisely, you cannot know exactly what the velocity is, and vice versa. So that actually, yung Boolean logic breaking down, that's actually very much also related to the Heisenberg's uncertainty principle. And to me, that is really the simplest difference between quantum physics and classical physics, the way we treat information. So as summary, so experiments are never gentle. Somehow naapektuhan yung ibang parts of your system. And quantum states, they are peculiar vectors. How peculiar are they? We write them like this. So in classical information, we have zeros and ones. In quantum information, we have a superposition of the zeros and ones, where your alpha and beta are now complex numbers. And that leads to a lot of interference effects na kung saan nanggagaling yung mga sinasabi nating advantages from quantum information. Okay, so that's the first part of my talk. But before I leave, I'll just recommend this book because I really like it. Quantum physics can be sometimes, I don't know, nakakatakot siya, pero this book really makes it easy to understand. It does away with all the strange stuff na most other books start with. This is the simplest that you can start with, and that's where the discussion I've done actually comes from. So if you're interested, highly recommended yung book na yan. Okay, so now I want to give an experiment that we recently did. But before I start, I have to explain to you how to make quantum states. So we have a lot of possibilities. We can now trap ions, as in you have an ion that is pinned to one position. We can have a train of them. We can also have superconductors. So this one, medyo involved engineering. You have to, well, actually both of them, you have to keep at very low temperatures to get the quantum behavior. And you can also have quantum states in atoms. So this is actually a picture of Mona Lisa, comprised of atoms of rubidium that we have here at UQ. Hindi ako gumawa, a colleague, Tyler Neely. So the quantum states I work with, they are made out of light, as in photons, particles of light, which have many different properties. One is polarization, like what plane is the electric field vibrating on. It can have wavelength or frequency, so that would define what the color is. It can also have time bin. So these pulses, they denote like at what point in time did your photon arrive. So we call them time bins. What I work with is, what property I work with? I work with the shape of light. So this is actually, when I was in UP, I did my master's with Vince. He was doing a lot of trapping, optical tweezers, using shaped light to control microscopic particles. I took inspiration from that, from the fact that I can shape light, and I use the shape of light instead of moving particles to contain information. So say this one would be a two-level system, so that's my qubit. If you have three different shapes, that would be your three different levels, and so on. So the shape of light then becomes a really versatile carrier of information, because it is conveniently manipulated using like room temperature devices, and you get to play with really a lot of shapes. They actually look like that in the experiment, kahit na simulations to, but if you do it in the experiment, they're actually quite good. So what's the relevance of that? Because this is your qubit. So qubit, we say two states, two components siya. Kapag meron kang shape of light, you can just define the 0 or 1 as one shape. And because we can have as many as we like. So meron kang cat that is dead and alive. Pag marami kang shape, pwede kang magkaroon ng zoo of a quantum state, because you can have as many shapes as you like. So in that way, the shape of light is really a very convenient qubit, because I can just increase the number of components that I can add quite conveniently. Kaya yung group ko sa UQ is called QDITs at UQ, because we can really make QDITs well. Okay, so yung so as I've said, yung shape of light as a thing, it's actually started from classical physics, from micromanipulation most popularly. So when I was starting in this field, there was a lot of work to do, making it, convincing the community that it is a really quantum carrier of information. So we did a lot of work there. I'll just put the references there. But the conclusion from all this work really is simply that we can measure the shape of single photons really well, and we can use it for quantum information. So we did a lot of quantum tests in all these papers here, that I think I can say now it is going to the mainstream as a quantum carrier. Kasi dati parang puro polarization, puro time bins. Ngayon, shape is really in the mainstream. So the work that I do, that I will present shortly, is work with my PhD student, Michael, and other physicists here at UQ. So Sally is actually a philosopher, and Andrew, the professor I joined with back in 2015. And that actually comes from a paper I saw back in 2011, kasi merong cartoon yung paper. And it had a very interesting title: Does ignorance of the whole imply ignorance of the parts? And I'll just ignore the second part. I don't have time to explain that. Actually, it was a long journey publishing this paper. Like, we had 2 rejections. This was the first review. Like, the reviewer really hated it because there was nothing state of the art, no pushing of the limits, etc. And then he replied, And we got this, oops, what's happening? I can't move my slides. Okay. Yeah. And then we submitted again. And I'm really happy, so happy with this review that I'm going to underline every word of it. So I think this theory paper got my attention because it's really something which I think can be accessible even if you're not a worker in quantum information. And I hope that's what I can convey with this next few minutes. We actually made it to the cover of PRL. So that was the cover of PRL last week. So we're very proud. We got picked up as well by Eureka Alert and FIS.org. So if you're interested, there are these two press releases there. So does ignorance of the whole imply ignorance of the part? So first, I have to share what is the whole and what is the part. So wholes and parts, the usual example in quantum physics is the entangled particle. So it's those two particles separated by a universe, but still they affect each other. But in our experiment, we have wholes and parts. In our experiment, we actually worked with something less exotic, which is the good old dit string. So when I say dit string, I have y0, y1 concatenated. So that's my whole. And then for the parts, I have y0 and y1 individually. What has the qdit got to do with it? So as you would guess, no, randomness increases as d increases. So if you think of a die, right, the more faces that die has, the harder it is to guess what face it would land up on. So we have somehow to measure ignorance, you have to measure randomness. Pero randomness is something that you have to measure in more than one shot, right? Like I really like this cartoon because it really shows you that you have to repeat and repeat and repeat to check randomness. So in this paper, they had a theorem. They called it mean entropy splitting inequality, which reads, for any dit string y0, y1, and an encoding of that dit string. So think of E as an encoding. So like maybe a paper where you wrote that string or some physical system which encodes that string. Okay, so given a string and the physical encoding of that string, there exists a pointer. So it's a random variable C, 0 or 1, such that this is true. It's more easily understood, I think, in the context of a scenario of a student and teacher. So say, magkuquiz yung student, ang tatanungin ay, ano ang y0, ano ang y1? So in a classical world, the teacher can always find out what is C. What is the C? Anong part ng string yung hindi alam ng student? So like at the end of the exam, the teacher can say, you don't know y0 or you don't know y1. So in the classical world, there's always that pointer to the source of ignorance of the student. That's what these entropies here mean. Okay. So E here, so siya yung cheat sheet na sinasabi ko kanina. Okay. So the teacher can always point to what is not known by the student. So in a way, it's a statement which says there is always a test that reveals which part of the dit string the student is ignorant of. Now, if you translate that to some task, you can test that theorem by giving the teacher this task, right? Find C that points to the part where there is large ignorance. So if you cannot find C, then you have violated that theorem. I like to show this slide because I think this is more mas concrete pag in terms of probability. So say meron kang string y0, y1. So these are just the big y's, they're just the sets. Okay, so meron kang d possibilities. And then you encode that in a notes E. So yung notes, D levels lang yung kaya niyang i-encode. So, meron kang D squared possibilities here, pero yung notes mo, D lang kaya. And then, tatanungin ka ng teacher with where, ano yung why not, ano yung why one. So, dahil meron kang D squared possibilities, tas yung cheat sheet mo, D lang, definitely, meron kang mawawala na information, meron kang part na hindi alam. And we will call the probability of guessing YC, given that you have this encoding and that the teacher asked for part C, as this conditional probability. So the theorem is there exists a pointer C such that your guessing probability is less than 1 over square root of D. And so we can, like, kumbaga, ito yung score. Na ito yung boundary natin. So how does the teacher spot ignorance? Magtatanong lang siya ng many questions, right? So if you're a student and you can have a cheat sheet, what is the optimal classical strategy? Isulat ko yung first part of the string, right? So say I always encode Y1. Then what would happen is, pag Y1 yung tanong, palaging tama yung sagot. Pero, pero pag why not yung tanong, huhulaan mo lang siya. So meron kang 1 over the probability of guessing it right. So yung strategy na to, it gives you a best guessing probability that is 1 kung yun yung kinodigo mo. Pero kapag hindi yun yung kinodigo mo, mag-guess ka at random. Okay? So para malaman ng teacher ano yung part na hindi alam, you just look at which part is it na 1 over D yung guessing probability niya. So this part here. Okay? Yeah, so this one, so as you can see, satisfied yung inequality na yan. Now, for a quantum strategy, what if you ask a knowledgeable friend like Einstein? So you have this quantum strategy. Instead of encoding just one part of the DIT, you encode this one. So this one is a superposition of the Y0 and the Y1. X and Z are the Pauli operators. Like, it's not important what they are. I'm actually going to remove that. I'll just put a picture. So this is the quantum encoding using the shape of light. So those are my DIT strings here, and that's what those encodings look like. So yan yung dadalhin ng student sa exam instead of 0 or 1. And what we find, magyayabang pala muna ako. So these are the sum of the encodings that we have for different level, for different dimensions. And as you can see, the experiment actually looks pretty similar. So these are our encodings for the 2-DIT string. So if you have that quantum strategy, the probability of guessing the first part becomes this. And the probability of guessing the second part becomes this. And that is actually, as you can see, neither of them is guessing randomly. Neither of them is 1 over D. So if you were the teacher, magtataka ka, bakit pareho yung guessing probability ng student? Hindi ko ma-identify kung ano yung part na hindi niya alam. So if you use that encoding, you actually violate this theorem now. Kasi 1, hindi mo alam kung ano yung C kasi pareho yung guessing probability. And also, yung value mismo ng guessing probability, it violates this. So the quantum strategy actually violates that mean entropy splitting inequality. So in a way, ang take home ay, if a quantum encoding is used, the teacher cannot find the unknown part. Kaya nung yung aming work, ang title niya, Hiding Ignorance. So you can hide ignorance, and more importantly, if you compare the classical strategy and the quantum strategy, so I'll just work through here. So ito yung classical strategy natin kanina, yung meron kang ini-encode na kung ano yung isa yun na isulat mo. If that was a 2-letter alphabet, you get 75% on average for a classical strategy. For a quantum strategy, you get 85%. And that actually increases more. Kung meron kang 6-letter alphabet, 58% na yung score mo kapag palaging isa lang yung ini-encode mo. Pero kapag yung quantum strategy na pinakita natin kanina, 70% yung score. So it's encoding in quantum gives you a higher score and you can hide your ignorance too. So that's it. So with a one qubit encoding of the 2-bit string, the student gets a higher score. The teacher cannot point to the part that the student is ignorant of, and the student can hide ignorance. Okay, so that's my second promise. Okay, last promise, situate where we are today in terms of quantum technology. So what we always hear, I think, yung palaging nasa news ngayon, mga related to quantum computing. But I think we have to clarify, what are quantum computers? Quantum computers, they are not just faster versions of classical computers. Like, in fact, quantum computers, they are not all-purpose computers. So they will not replace our classical computers. Quantum computers have known advantages for very specific problems. Actually, it's a very active field of research, yung paghanap ng mga problems na magkakaroon ng advantage yung quantum computer. Merong dalawang very popular. So the first one is yung tinatawag na Shor algorithm. If you use a quantum computer, the runtime is very much less compared to a classical algorithm. And yung other problem is a search problem. So yung Grover algorithm, it's a database problem. Given I want to find X in this unsorted database, gaano katagal mo siya hahanapin? Using the Grover algorithm in a quantum computer, you have this quantum speed up. So yan yung dalawang very popular na known advantage for very specific problem. And they are very important problems. Very important. Like, for example, yung Shor algorithm, it's actually an algorithm for factoring. Now, why is factoring interesting? Because, so say if you just want to take the product of two numbers, you do that, okay? You get that product, madali lang siya. Pero kapag tinanong ka, what are the prime factors of 661,643? Suddenly, hindi siya madaling gawin, di ba? So this actually is the basis of, so actually the factors are this one, no? If you have photographic memory, those are the factors. So ginagamit yung factoring, yung the fact that it's difficult to factor is actually used by our crypto systems right now. Like yung mga banks, yung every time you put a pin in the ATM, that actually goes to the RSA algorithm. So if someone can factor big numbers, that would really break security big time. Fortunately, wala pa tayo sa panahon na yon. Kasi if you look at this graph, so what's this graph? This is the time to factor an L-bit number. So like by 2030, NIST in the US suggests na dapat mga 1,200 bits na yung fina-factor na number to maintain security. So as you can see, it's very hard to factor that long. Meron ito yung mga possible Shor algorithms. Note na ang promise dito, meron kang quantum computer na 2L squared logical qubits. So like you need a quantum computer with 1 million logical qubits para maging at par ka with what we have right in 2030. And we are very far, I must say. Because yung quantum computers today na ions, yung mga sinasabi ng Google, ng IBM, mga superconductors na yan, they talk about qubits, the qubits as in physical qubits. These are not logical qubits. Para magkaroon ng logical qubit, depende sa estimate, sometimes it's like 1,000 physical for every one logical qubit, which is really a lot of qubits. So I would say breaking factoring, breaking using Shor's algorithm is probably not the first application of the quantum computer. The first application would most probably be, I'll skip that. First application would probably be simulations, because if you want to simulate a quantum system, it makes most sense to use a quantum system to simulate para hindi mo na feed yung quantum behavior. They naturally behave as a quantum system. And I think that's where we will see the first applications sa pag-model ng configuration ng molecules, things like that, hopefully. Quantum communication, yun yung mas maraming advance. I think. So for example, meron ng intercontinental quantum communication satellite. So 3 years ago, we had the most secure video call ever between China and Vienna. Pero kilobytes per second rate siya. So hindi siya kasing bilis ng what we are used to with our standard technology. So siguro gagawin mo siya for those really very high-end communication that you need to be really secure. Kasi meron pa siyang bandwidth problem. Yung isa sa mga favorite ko na application ngayon ay itong tinatawag kong quantum scrambling. So this is actually Quintessence Lab. That is an Australian company. I met the founder of this back in 2008 in ANU when I visited Vince. I'm so happy to see they're doing very well. So what they do is, you know how we have a lot of information now that we store to the cloud. So when you store something to the cloud, hindi mo alam nasaan siya, di ba? So kung merong maka-break dun sa kung nasaan man nakastore yung cloud physically, pwedeng manakaw yung information mo. So pwede kang mag-add ng additional layer of information by first scrambling your, say you have a legal document, you scramble that information first using the device that you buy from Quintessence before mo siya i-save sa cloud. So in a way, kahit na may makakuha ng information mo from say iCloud or Amazon, hindi nila makukuha yung legal document mo kasi kailangan nilang pasukin yung law firm mo para i-unscramble muna yon. So this is not like quantum, but it is classical thing that we are doing that is scaffolded by something that is quantum. So I think yung path to quantum technology should have these baby steps. We find things that we can first scaffold with quantum technology before we can really go full-blown quantum. And how long that would take, I mean, I really don't know, but I think the field's moving really quickly. It's exciting. Okay, so I think that's all the time I have. Just take home. Experiments are never gentle. Quantum states, they are different from classical states. You can hide your ignorance using a quantum encoding for a 2-digit string. And quantum computing and quantum communication, they're developing really rapidly, but there's a lot of problems for physicists and engineers and for everyone really. Okay, I think that's all.
Okay, thank you very much. Yeah, thank you very much, Jack.
Walang tanong sa chat.
Not yet. Maybe they're all trying to absorb it. Maybe we should ask. Maybe we should volunteer Vince to actually ask one of the questions. Yeah.
Very nice talk, Jack.
Yes,
actually,
yes.
I blame Vince for me being in this field.
Blame
well,
her
no, blaming Vince for giving me the tools to be in this field.
Yeah, I'm sure he's very proud of you.
So I'm throwing first question, Jack. I like it when you said that we're fighting or looking for answers or problems the quantum technology can solve, right? So when you said it's like a solution for a problem that does not exist, is that the way how you? you explain it?
That's a controversial question. Okay.
Okay, but that actually is the question that was raised for the laser. It was a solution for a problem that doesn't exist in the 1900s, but in 50 years there was a solution.
No,
So
okay.
it became very popular. So I mean, I'm not negative to that. That's really good.
No,
But
so the,
my question actually for your experiment.
oh,
In your experiment, you said you used different orbital angular momentum
we
to
use
distinguish the qubits.
Yeah, you're a bit choppy, Vince.
yeah, choppy. Yeah, so we used Laguerre-Gaussian modes with same V phase for every. So say we pick we pick D modes that would have the same V phase, and then
Okay.
that's
So
what
did
we
you
combine.
ever? Okay, so did you try to interfere different Laguerre-Gaussian modes and have a combination of qubits by the interference?
No, so we have only one SLM. Like we encode there what we would need to say do a superposition of the five Laguerre-Gaussian modes. So it's not necessarily it's not L1, L2, L3. We really used both the L's and P's.
But there's also L and negative L. So when you interfere both L and the negative L, you get a
We get
Hermite.
Hermite. Yeah.
So is that another qubit when you have an Hermit Gaussian mode?
No, I don't think so. So what happens is you, at the start of the experiment, you fix the set of modes that you want, and then you use that. If you choose another, like it doesn't matter what modes you choose. Like say if you have a 2 level that you use a +1 and a -1, that's no different from a 2 level where you use say superposition of +1 -1 and superposition of +2 -2. So it's something that we fix at the start. Yeah. And then I'll just like to comment on the okay, so sure, factoring algorithm, that's a problem that exists. Searching through a database, that's a problem that exists. Showing a quantum advantage there practically is hard, so people don't do that. So ang nakikita ko ngayon kasi sa field, ginagawa nila, merong mga problems like solving the permanent of a matrix. That's what all those boson sampling problems na last year got a lot of news. That's a good problem, but I must say parang para sa akin artificial siya. Pero may quantum advantage doon. But yeah, it's a way. There's a question. Hi, Michael.
Yeah, I think Michael. Yeah, let Michael do it.
And I first of all, very nice talk. I learned a lot because I hear the buzzwords. It's the first time I think I kind of understand what's going on. But I've heard quantum cryptography as one of the applications of this, and maybe in just a few sentences you can explain how that works.
So the quantum cryptography, actually yung pinakita ko na satellite call between China and Vienna, that's actually quantum cryptography. So what happens there is you have a key. So it's a key that you share dun sa dalawang stations na yun. And this should be what we call parang entangled particles. So it's like if you measure something on this part, the other person on this part knows what it is. So pag quantum cryptography, kailangan mo ng entangled particles that you would share, and you need classical communication as well. So it's like the other person should know what you have done. Okay. Tapos kapag i-compare mo yung ginawa, so dahil alam mo yung ginawa niya, meron kayong parang list of things that you expect. And if you find na, bakit masyadong maraming mali compared to what I expect, yung conclusion mo is that may eavesdropper in between. So kapag marami kang error na nakita doon sa list mo, sasabihin mo na, ulitin natin kasi baka may
So you can also
eavesdropper.
detect if somebody's eavesdropping.
Yes, so may nadidetect mo yung eavesdropper. So secure siya, yun yung sinasabi na security ng quantum cryptography. Hindi mo siya mahahack, it is hackable, pero madidetect mo kung nahahack ka.
Oh, okay. Okay, thank you.
Yeah.
Okay, let me take some questions from the YouTube channel. We actually have people
Okay.
watching there. Okay, so one comes from Raymond Tan. So his question is, can the ignorance detection technique be useful for gauging the performance of artificial intelligence?
So kung imbis na teacher, artificial intelligence yung mag-check? Depende what is the input to the artificial intelligence. So like as you've seen in my talk, if you look at the probabilities, pareho sila eh. So kung probabilities pa rin yung i-feed mo sa artificial intelligence, you're going to feed them the same numbers. So in a way, it might not be useful. Siguro kung i-feed mo yung kung may access ka to the cheat sheet of your student.
Yes.
Yeah.
Okay. All right. The next one comes from Al Serafica. What are the possible applications of quantum technology in the Philippines? For example, maybe in agriculture, health, environment, or advanced materials. And he has a follow-up on weather modeling. Like path of a typhoon requires a lot of computing capacity. Can quantum computing help with that?
Yung mga computational problems na very general, I think that would need a lot of work kasi hindi talaga yun yung mga problems na hinahanapan ng advantages ng community. So I would say classical computers pa rin doon. Pero application, so kunwari dito sa Australia in recent times, ang daming against doing my digital health record kasi natatakot sila na yung kanilang health record isa-store mo sa cloud tapos mananakaw. So I think doon pwedeng pumasok yung sinasabi ko na quantum scrambling. So meron kang talagang process na yung pagka-random niya galing sa quantum physics. So hindi mo talaga siya ma-unrandomize kahit na ano pang gawin mo. So yun yung i-store mo sa cloud. So that would help appease yung mga security issues, di ba? Yung mga, okay, pag sinabi mo siguro na ika-quantum scramble muna natin bago natin ilagay sa cloud. So maybe maging mas pervasive yung mga digital health records. Like, I don't know, it's one low-lying fruit.
Okay, yeah. In connection with that, before I go to Raymond's follow-up question, since you mentioned about scrambling the information before you store it in the cloud, is it a one-way process or like what if you need to retrieve information?
Okay, so
will it also be done?
Mariretrieve mo siya kapag meron ka nung device. So like yung quintessence, they sell you a device na before it's a PCI slot sa computer. So if you have that, you can unscramble it.
It's like a key.
It's like a key, exactly. So yung magnanakaw, hindi lang niya kailangan i-access yung cloud, kailangan i-access niya yung computer mo sa law firm mo kung nasaan nandun yung key.
Oh, okay. Okay,
so,
thank you. So here's the follow-up from Raymond about the question on AI. What he means is that the AI is the student.
The AI is the student. Okay.
Yeah, so like a Turing test to figure out how smart the AI is.
Yung mean entropy splitting inequality na yun, nag-a-apply siya for all classical information. So I think kung hindi quantum information yung gagamitin ng AI, I don't think it's possible. Pero yeah, yun lang ang aking feeling.
Okay, thank you for that. So do we have any more questions from the audience? Okay, that was a really great talk, and you managed to pack in a lot of information.
Oh, sorry, na-realize ko naman ako parang ang dami kong sinasabi. Pero okay.
Hi,
yes. Who's there? Giselle. Okay, yes, Giselle, please.
Hi, Ma'am Giselle.
Hey, how are you? It's great to see you.
Yeah, thank you for coming. Yeah.
Very basic, simple question, and I wish that. First, Francis Paraan is doing some work on quantum computing as well. He's with NIP with physics, and then of course Nath Hermosa.
Actually, Nath. Yeah.
Shaping light, And then, of course, the basic question is the speed of light constant? And
It is constant, but it can be less than c.
it can be less than c. That's the part that, I just want to clarify, because I understand that the speed of light is no longer constant. And it can be shaped or affected by something, right? So anyway, I wanted you to explain that very basic thing, Jacqui.
So yung sinasabi kasi natin na speed of light as c, nag-a-apply siya for light that is a planar wave. So kung magdo-drawing tayo ng light beam, di ba? It's a straight line. So pang straight, ibig sabihin nun, yung mga shape niya, yung plane siya. So parang if you were looking at the face front, those are planar. Yung mga pinapakita ko kanina na shaped beams, if you look at the face fronts, they are curved. So it's like parang isipin mo yung light na parang pila siya ng mga soldiers, nag-a-advance sila. Yung light na sinasabi mo na C, yung pila ng soldiers, straight sila. So march, straight. Kapag nag-iba na yung shape niya, yung pila ng soldiers na yun, nako-curve siya. Pag nag-curve siya, nagiging slightly less than C na siya. And that is a wave effect. It's actually not a quantum effect. Wave effect siya. Kasi para mag-curve yung pila ng soldiers na yun, yung rays, parang siyang from the interference of many planar wave components. So it's actually a very small effect na na-measure lang namin dahil we were working with single photons. But it's not a quantum effect. It was just at that point convenient to use single photons. But it would apply to any wave. So kunwari yung sound waves, the more curved it is, kahit sabihin mo pa na 340 meters per second siya in air, kapag iniba mo yung shape ng wave front ng sound, it would be less than that. So dahil siya sa shape, yeah.
All right, Jacqui, how I wish that you could continue to lecture this way to our physics students.
I'm willing to.
And the faculty are. I'm glad Vince is around. But what about the other PAASE members? Anyway,
yeah, they can access the recording and they can always get in touch with Jacqui if they have more questions.
Okay.
And if they want to ask her to guest lecture.
Yeah.
Yeah, I can. Yeah.
Wonderful. Thank you.
Yeah, I have one question. So you've mentioned that the development in this particular field, I think, is speeding up, right, in the last few years. So what are the current challenges to, to really increase the capabilities of qubits and to increase the speed of computing?
Ang greatest challenge talaga ngayon sa quantum computing is quantum error correction. So like Google, IBM, they can produce, say, as many as 1,000 physical qubits, like even 100,000 naririnig ko. Pero kung hindi siya clean qubit, kasi yung qubit, once you like put it out there, there's always a probability na magkakaroon siya ng error. So parang computer natin, di ba? Meron tayong DRAM, may mga ginagawa tayo para i-minimize yung error. So yung quantum computers, kailangan din yun ng ganun. And that's very hard. So like ang estimate is para magkaroon ka ng one perfect qubit, yung most modest kailangan mo ng 1,000 other qubits. So kung gusto mo mag-operate on one perfect qubit, kailangan mo ng 1,001 physical qubits. And that is just not around right now. So ang Google nagpo-promise siya ng up to 100,000 maybe. Pero even then, hindi ko siya nakikita paano siya mag-scale unless we really be very smart na kaya mong mag-error correct with one other qubit maybe. Something that's mas scalable. So yun.
So when you talk about physical qubits, so this is like infrastructure, is it?
Oh, so like in your chip, meron kang one qubit doon, pero yung qubit na yon, that's noisy. Kaya yung naririnig natin ngayon, noisy intermediate quantum systems. So para siya maging clean, kailangan mo ng other qubits to correct it. So yun yung wala pa ngayon. Wala pa tayong quantum error corrected qubit na yun talaga yung kailangan para magawa mo yung madaming mga pinapromise. Kaya yung community ngayon naghahanap ng what can be solved with a noisy quantum computer. That's also another active area. What can you solve with imperfect quantum computers?
Okay, so we have another question from Angeline Lau in the YouTube. Correction of errors using coding theory concepts. Is it possible or what?
Okay, so hindi ako expert sa quantum error correction, pero yes, something like coding theory, yung mga I forgot, mga CS10, yung mga ganon, yung yeah, okay, I won't say anything, pero ano siya?
But it's it's an
Very
emerging or
active
ongoing
field siya.
field also.
Very active field siya.
Just-
Yeah.
Okay, so thank you very much, Jacqui. Do you have any final comments for our audience? Maybe final words.
Thank you for coming.
Yeah, I think
Oo,
this is
maaga.
yeah. No, I really hope that yeah, people get inspired about the work that you do. I don't think I think we need more people doing this kind of thing. Maybe it's not so accessible for people in the Philippines. What do you think? Would you know like
Actually-
what's the current state?
Actually, ito actually yung fear ko eh. Kasi yung quantum technology, mangyayari siya. I don't have a doubt na mangyayari siya. So ang mangyayari kapag nangyari siya, magkakaroon na naman ng division in the world. Those who
Okay,
invested early and those who did not invest. At nakikita natin siya ngayon, di ba? Nakikita natin
Yeah.
yung mga nag-invest early sa technology na nag-fly. Meron talagang lag. So, hindi quantum computing, kahit na hindi siya something immediate, it's something that we need to think about. And may mga small ways that we can contribute. Like, math can do something. Yung experiment ko actually, that is something I think doable sa NIP. So, I think we have to get involved. I just don't know what the path is.
Okay.
Yeah.
Okay, wait. I'm just waiting for another question. So Raymond mentioned that he wants to have another question. So while we're waiting for that, maybe
Yes.
I'd like to ask. So do you happen to have any graduate students from the Philippines, or are you currently mentoring?
I am actually looking for a student.
Okay, so that's a shout out to all those who are interested to take up graduate school. So yeah, maybe you can reach out to Jacqui.
Yeah, I am actually looking for a student. Yeah. Email
Okay.
me.
Great. So here's the last question from Raymond. Would you care to comment on the opportunity to do relative low cost basic research and development in theoretical physics in a resource constrained country?
Quantum error correction, I think we need a smarter way to do it. And that takes pen and paper and understanding of some deep maths and coding theory, which is probably too late for me to get onto. Pero ang quantum error correction, I think it's open, wide open. I don't know kung meron yung sinabi ng Google na, okay, ganito kami magka-quantum error correction. I don't think meron ng contract na ganon. So, I think exciting field siya. And also, I think yun nga, the next big thing is dahil ang mga companies, hindi makagawa ng perfect quantum computer. Ano yung problem na kaya mong itackle with a noisy quantum computer? Kasi nung inisip yung Shor algorithm, yung Grover algorithm, you imagine the best eh. Kasi siguro dahil masyado pang malayo eh na, wow, okay.
It was an ideal situation. Yeah.
So ngayon, we are in a world where there are noisy quantum computers. So what can you do with that?
Okay, great. So
and again, that's pen and paper.
Okay, Vince has something to say.
Yeah, let me add to that comment. The experiments that Jacqui is doing is actually using light and using not ions. Ions will be an expensive quantum experiment. You need to have a cooling system, you need to have a lot. But yung light na ginagamit ni Jack can be done in the Philippines. We've already have a lot of equipment that we purchased long time ago that, it's still in UP, for example. And I think LaSalle also has a lot of, the physics department has the same equipment that we have. And they can use it for similar experiment that Jack is doing.
Yeah. Yung palaging comment, actually yung experiment na pinesend ko, ang comment lang doon palagi, dahil nga sa laser siya, ano yung quantum doon? Pag meron kang single photon detector, maa-argue mo yun sa reviewer. So, kunwari sa setup ni Taning, maglagay ka ng single photon detector, quantum experiment
But they
siya.
already have that. I mean, they can.
They already have that? Okay,
I
okay
think
na.
they can. Yeah.
So, they can do it.
They can do it.
Yeah.
Okay, thank you. That's great. Yeah, it was really an inspiring talk. Thank you for that, Jacqui. But do you have anything else to say?
No, thank you for coming again. That is good.
Okay, but before we end, I want to plug our next webinar. So let me just share my screen. Okay. Okay, so thank you for coming to this particular talk, and I do hope that a lot will be inspired to follow the footsteps of Dr. Jacqui Romero here, who has really been very successful in her field. So next week, instead of just having one speaker, we will have a panel. Well, maybe one or two will be speaking, and then we'll have a panel for discussion. So this is a follow-up on the work that was initially presented by Dr. Krista Yu on post-pandemic recovery strategies. So we've actually managed to get some funding together with our colleagues from Malaysia. So next week, we'll talk about some of our results on post-pandemic recovery strategies for the agro-industry sector in Malaysia and in the Philippines. So we'll be on the same time. So it's July 17, Friday, from 8 to 9 a.m. So for those of you who are interested, please register at tinyurl.com/GCRF 2020. So this is really collaborative work from different institutions in Malaysia and in the Philippines. And then again, I'd like to make a shout out that we will be having the 40th PAASE anniversary and 2020 annual PAASE meeting and symposium from July 20 all the way to August 14. So during that period, we won't be having the webinars, but we will have several lectures integrated into the program of the 2020 APAMS. So we will be having sessions from Mondays to Fridays from 8 to 10 a.m. Philippine Standard Time. So we've already passed the deadline of the call of papers, but you can have a look at the program in our website at paase.org. So again, the Philippine American Academy of Science and Engineering, you can access us via Facebook. We have our official PAASE Facebook page, and our website is thepaase.org. And all recorded webinars will be uploaded in our YouTube channel, which is PAASE Webinars at bit.ly/PAASE Webinars. Okay, so that's it. So if there are no more questions, no more comments. So thank you so much. Thank you again, Jacqui,
Thank you.
for being our lecturer today. Thank you. Bye everyone,
Thank
and have a
you.
good day ahead.
Have a good day. Thank you.